Hi, so you're working on Lab 9, LR and RLC circuits. So in this video, I will explain the experimental procedure and the equipment that you're using basically, and give you a couple of hints in order to complete the lab report. So in this lab, if you were in the real lab, we will be using this Pasco RLC circuit board. I think you used this once when we having the real lab classes. So you must be familiar with this circuit board. Anyway, so in this lab, we will be using RL. R is the resistor, L is the inductor, right? So we'll be using a 10 ohm resistor, 10 ohm resistor, and then the inductor, which is 8.2 millihenry. And also in the second part, we will be using a capacitor as well. So in the lab manual, you might be seeing a picture like this one. So that's basically the schematic diagram of this RLC circuit. So in the part one, what you're going to do is you're going to have a resistor, inductor connected in series to the power supply. So this picture shows you the circuit diagram. So the power supply, then the resistor, and then the inductor. And then we will be providing the circuit with the square wave input voltage. Then we need to connect the resistor to a voltmeter where we're going to measure the voltage variation across the resistor. And also we need to measure the voltage variation across the inductor. So we will be connecting these two pieces, I mean the resistor and the inductor, to the Pasco interface, and we can measure or analyze the variation of voltage across the resistor and the inductor using Pasco capstone program. So basically we are using the same capstone file as we used earlier. So we will be seeing the voltage variation across over the time. Well, in the part one, you need to measure the resistance of the resistor, even though it's given, it's labeled on the circuit board as 10 ohm, but we need to know the real value. So basically we are measuring the resistance across resistance of this resistor using a multimeter. So when I measure it, it's multimeter read 10.9 ohms. However, it was a little bit fluctuating around. So maybe there's a little error in the measurement. So multimeter just jumped around about 0.1 ohms or so. So there's a error factor, adding an uncertainty into our experiment. Anyway, so the R measured is 10.9 ohms, even though it's labeled as 10 ohms. Well, so we're going to use the RL circuit. So resistor and an inductor in seriously connected to the power supply. So when we collect the data on the Pasco capstone file, the first graph is showing the voltage across the resistor versus the time graph. And the second one is the voltage across the inductor versus time. And this is the output voltage. So we are providing the circuit with the square type input voltage, I would say. So here, so you can analyze this graph, like what's really happening here. As you see here, the voltage of the resistor, voltage across the resistor changes smoothly, right? So here is a smooth exponential increase, and it's come to a steady state max, right? While the inductor shows us really a spike here. So it's jumped. It's not a smooth increase, but it's a jump over here. And then it decays smoothly, but it's not going to zero voltage. See, this is the zero voltage level. It's really not going to the 0 volt, but it's come to a steady state in a non-zero voltage value. Then here, the voltage, like after a little while having the steady state maximum voltage, the voltage across the resistor decays exponentially and reaching to a 0 voltage here, right? And then if you compare that variation with the variation at the inductor that at the same time. Now you saw that it came to a non-zero steady state voltage, but here it is not going to zero. It's quickly jump into a maximum negative value, as you see here. So it's jumping into a maximum negative value and then it's decaying back. But again, it's reaching to zero, right? So it's decaying back to zero. And it will continue to repeat. So you will be seeing the same variation will be repeating again. On the inductor also, the voltage variation will repeat. Well, when you're doing the analysis, so in the second question, you will be deriving the equation for the voltage across the resistor and the voltage across the inductor. Anyway, so you may have noticed a equation quite similar to this one. So here, in the inverse exponential fit, the equation reads a 1 minus e to the power b t plus c, right? And the a value and the b value are given here. Okay, so you may read those numbers on this provided data. Anyways, and you may compare this equation with the known equation. So in some point when you are deriving the equation for the voltages, you might have noticed an equation like this. So it's Vt Li over tau e to the power minus t over tau plus V naught. So compare these two equations, quite similar, right? So the A value on this graph, it's 49300. So that value is equal to the A, and that A is equal to Li over tau. Okay, then e to the power minus bt, and on the graph b is 2000. Here on this equation, that b means 1 over tau, right? So 1 over tau is equal to b. So using that equation, you may solve for tau. And then the y naught value, here it is c. So c is equal to 0.003, and that is the v naught. So that's the uncertainty. So when you are starting the experiment, there was a maybe there was a little initial voltage there, right? So likewise, you may compare these exponential fits with the derived equation that you did in the second question. Well, in the part 2 of the experiment, we are going to introduce a capacitor into the circuit. So you're going to connect a resistor, a capacitor, and the inductor in series with the power supply. Again, we're going to send a square wave input voltage. Now, let me go back here again. So basically what we're going to do is we're going to connect a voltmeter or connect the two sides of the inductor, capacitor, and the resistor into the interface, and then we can collect the data, the voltage variation with the time. So after I collect the data, this is the graph that I obtained. So as you see here, the first graph is the voltage across the capacitor versus the time graph. The second one is the voltage across the inductor versus the time. And the third one is the output voltage. So we are sending a square wave input current, and we are measuring the variation of voltage across each piece, right? So here, we see the voltage across the capacitor smooth, right? It is a smooth exponential increase. And then if you see the voltage across the inductor, there's a spike, and then it's dropped exponentially and reached to the 0 voltage. And here it's the voltage across the capacitor exponentially increases to the maximum. And then the voltage of the capacitor decreases exponentially to the minimum 0 voltage. At the same time, the inductor spikes in, the voltage of the inductor spikes into the maximum negative value, and it's exponentially decay into the steady 0 voltage, right? And then it repeats back again. So here, kind of, the capacitor is breaking the circuit when it charges. So in steady state, there's no current this time, right? So here at the steady state, it's in the maximum value here. And here at the steady state, at the 0 position, so there will be no current there. The we see the voltage across the capacitor follow the similar pattern as the resistor voltage that did earlier. So you might be observing like it's about the same curve, kind of same pattern. But if you notice really closely, the with the resistor, we saw a pretty steady maximum value. Here, we don't see that steadiness. So when we are doing the experiment, we didn't take the resistance of the coils into account. So it might add some uncertainty into the experiment. So it is another error factor. So when we did the experiment, we measured this resistance of the coil and we found it to be 6.5 ohms. So the total resistance in the circuit should be 6.5 plus 10.9. So total resistance is 17.4 ohms, but we didn't consider that resistance into our calculation. So it might give a uncertainty in the experiment. So I believe this will help you to answer the questions on the lab manual. If you still have questions, you may meet a TA on a Zoom meeting or email your TAs. All right, so thank you. And oh, one more thing. So when you are completing the question 2, so you will be seeing a table like this. So don't worry about adding numbers, like applying numbers in that. Just solve it in an equation format. So it is okay to leave equations here. We don't expect you to solve for something and have a number in there. So we don't need any numerical values. We need the equations for voltage across the resistor and the voltage across the inductor. So whatever the equation that you're getting here can be compared with the exponential fitting curves that you had on the data, right? So basically, when you're solving for the voltage of the inductor, you might see an equation very similar to this one. So please use Professor Capuano's theory video above this video. So she will be explaining the theory behind this experiment. All right, so thank you, and I hope this will help you to complete the lab successfully. I'll see you next week.